All right, so now we move on to lesson 12, which is the second lesson of dynamics, and it focuses on the problem solving, or actually introducing numbers into this theory that we've introduced from lesson 11. So in lesson 11, we talked a lot about the Newton's three laws of motions, which are his first law, second law, and third law, where the first law says that F net is equal to zero. The second law says that there's an unbalanced force causing some sort of acceleration in the given direction of that net force. And then the third law saying that if we apply a force, there is an equal and opposite reactive force in the opposite direction. Now, in terms of lesson 12 here, what we're going to do is we're primarily going to focus on the approach dealing with second law, or when F net is equal to ma and there is some sort of acceleration. Now, as we get into the notes here, something to highlight is that the net force, or the resultant force, is the vector sum of all the forces acting on an object. So it is the combination of the vertical and the horizontal, or even the slightly angled forces that are being applied to problems. And you're going to see what we mean by that. Now, net force is not something you directly see because it's the result of a bunch of different forces coming together to cause motion, but we want to think about net force as this object of net force is the resulting effect of all of the forces coming together in the horizontal, vertical, or angular or angled directions. So you're going to see that in these problems, we're going to put together a bunch of forces. Through that sum of the forces, we get some sort of overall resultant, and that resultant is a net force that causes acceleration in a specific direction. Now, something we're going to need to do very specifically within these problems is talk about free body diagrams. Free body diagrams are diagrams that include all the forces, or a body diagram that includes all forces acting on an object, regardless of if they cause direction or not. Because when we talk about net force, we may have some sort of force that is in the east direction, some sort of force in the north direction, and then some sort of force maybe in the west direction. Just because it doesn't cause the overall result of what happens, we still have to make sure that the object accounts for all the forces that are on that object. And so eventually what the free body diagrams lead to is that they allow us to determine the net force on an object, or the sum of all the forces. So free body diagrams, there's a couple examples below here, some simplistic ones here. Namely, if I have some sort of object on a horizontal, I'm even going to draw the horizontal in blue here. Suppose this object is on a horizontal and the object is represented by the dot. Well, there'd be some sort of FG, or gravitational force, and the gravitational force against that horizontal surface would result in some normal force, which is the contact force between the surface and the object. All right, so in that case, we would say Fg equals Fn, and they balance, therefore the object wouldn't be moving vertically in that first situation, or namely this situation here. What if we then introduce, though, some sort of applied force in the horizontal? Well, Fn and Fg would still be balanced, but this odd Fa here determines the net force, because if these two forces balance with each other and the F net is equal to zero in the vertical direction, we now have this unbalanced force that is this actionary force in the horizontal. So we're going to get more into that when we come to the examples, but just know that free body diagrams are the diagrams that include all the vector components of the forces that act on an object. Now, something we want to note here, just out of the one example before we actually go into our own examples, is the fact that if I have balanced forces like Fn and Fg, these things cause no vertical acceleration. So I'm not going to see the object fly off into space, and I'm not going to see the object crash down through the floor. If they're balanced, we know that by first law, this object has some sort of inertia and it wants to stay exactly vertically where it is. Whereas if I look at the x direction, the Fa is greater than the Ff. And in this case, if the Fa is greater than the Ff, I'm going to note this here, Fa greater than Ff, it's going to accelerate in the direction of the Fa. So I'm even going to put that the acceleration causes the object to move in the right direction. One last thing before we get to our specific problems from here. Looking at the example below, we know that the F net of this would be equal to Ff plus Fa. The reason is because Fn and Fg are completely balanced. If these forces are balanced, I don't need to include those somewhere in my F net statement, because they would eventually cancel each other out and be zero. Whereas I have an unbalanced Fa with an unbalanced Ff, or a greater magnitude Fa with a lower magnitude Ff, if I put those things together in my F net statement, they're going to represent that unbalanced net force. Now, you're probably thinking, when you look at this here, what is the difference between here and here? The difference comes down to these vector symbols right on the top. And I'm going to even highlight that here. Boom, boom, and boom. There's a vector symbol right on the top. If I drop that vector symbol, I have to recognize that it is like me doing the following. F net is equal to Fa, which is positive, and I'm even going to put that in here. This is a positive force. The FA goes in the right direction plus the negative FF because the FF opposes the motion. Now, when I drop the signs of these things, or when I combine the signs, I should say, I'm going to get an FA minus FF. And so that's where they get that line from. When they go from the vector arrow on the top indicating that this has direction to then actually implementing the direction, they just drop the vector symbol on the top and then they shift in the actual sign of the motion within the algebra here. Now, for most of these problems, I'm actually going to stick to this first one here. And then the later and later our lessons go, I may start to do this just to show you what the complement of what it means to drop the vector arrows on the top and rather put in the signs indicating direction. All right, we're going to skip forward a couple pages here. We are going to go to our first example, or the first in-class example, which is the following. A 6 kilogram cart is being pulled by a horizontal force of 25 newtons. If the frictional force is 15 newtons, what is the acceleration on the cart? Okay, this is pretty typical in these problems, looking for acceleration. First and foremost, if they give you a 6 kilogram object, you're going to write in that you have mass, so you're going to write an m above that. They give us a horizontal force or something being pulled with a horizontal force. That means that this is symbolic of our FA or our applied force. If the frictional force is 15 newtons, you're going to put FF here representing the frictional force. What is the acceleration of the cart? So acceleration equals question mark. All right, first and foremost, we want to draw out our diagram for this, or our free body diagram, our FBD. So I'm going to draw the horizontal and I'm going to draw some sort of cart. It's not going to be super artistic, but it will do the job. There we go. So we got a couple wheels on that thing, cart going on this path here. Now, we know what we want to do with this, and that's what we want to draw our free body diagram that includes all the forces. In this case, the FF is smaller than the FA, and so I'm going to write the FA here, or the applied force, the pulling force, and then I'm going to write a smaller arrow representing the magnitude of the force of friction. So this is going to be force friction. There we go. Now, the arrow length itself tells me that the magnitude is one thing versus another. I don't need to actually put the direct magnitudes on here as long as the arrows are proportional or slightly proportional as best as we can to those different forces. That's good enough for us. So the FA is greater than the FF. Now, the other forces you may be forgetting here are the following. You have some sort of FG, which is the force due to gravity pulling the object down towards the surface of Earth. But then because it's on a surface, the contact surface gives us this idea where we have a perpendicular force, the normal force, which opposes that and says if there's an FG force, it responds back with this Fn, or the normal force that is a perpendicular angle to at 90 degrees to the horizontal. Now, here's our diagram. The one other thing I may encourage you to put here is an index indicating positive direction and negative direction. If you don't think to do that, I would definitely make sure anytime you're drawing a free body diagram, you're putting the positive and negatives, or else how do I know which way is positive or negative? You just wouldn't, simply. Now, here's where we go from here. If you draw your free body diagram, the next step is always to write your FNet statement. And so I'm going to go off to the side of this, or to the right, and I'm going to write FNet with the vector symbol above is equal to the action force, or the FA, plus the force of friction. And both of these are going to have the vector symbol because we need to assign direction to both of these, including the FNet. Now, from here, what I'm going to do is I'm going to expand out the FNet from our formula sheet and say FNet equals mass times acceleration, which is equal to FA, or the action force, plus the force of friction. There we go. Now, from here, what we're going to do is we're going to isolate for our acceleration by dividing by m. And so I'm going to take both sides, divide them by m. This is going to give me acceleration is equal to FA plus FF, making sure I put vector symbols on both of those, divided by the m. We do not drop the vector symbols until we've either substituted the number in itself or we've assigned the sign directionally to both of these quantities. But because we hadn't assigned any directional quantity to these yet, we're just going to leave them as FA with the vector symbol, FF with the vector symbol. Now, to wrap up this problem, what we need to do is figure out the acceleration by actually plugging in the magnitudes. For the first one, positive 25 newtons because it was moving in the right direction, plus negative 15 newtons, which is in the left direction or the opposing direction, divided by the mass, which is 6.0 kilograms. Now, as you can see, I'm putting in not only the vector sign indicating direction, I'm putting units for everything, and I'm making sure to include the full number. Therefore, my acceleration is equal to, when we simplify this, I'm going to get the following. 25 minus 15 is 10. And 10 divided by 6 is going to give us this answer of positive 1 point. And because it's two significant digits, you could technically write this as 1.67, but we want the two sig digs, so I'm going to write 1.7 meters per second squared. And do you see how I wrote that positive? The positive is indicating that the acceleration is in the direction of the net force. What is the net force direction? It's towards the greater force in the horizontal. So be very, very specific about that. Okay, now we're going to go on to example 2 here. Example 2 says that we have a 5 kilogram object that is experiencing a 15 Newton force north, 25 Newton pulling east, and then a 20 Newtons force pulling 30 degrees east of south. What is the acceleration experienced by the object? Okay, this is just a slightly more complicated version of the last one, but you're actually going to see that there's a lot of parallels between the unit that we just did, which is kinematics, and this example here. Now, what I'm going to recommend you do is I want you to draw out a free body diagram where you can draw a circle, a box, or whatever. They just said this object. So I'm going to make sure I just draw in a little box here. Now, we're going to indicate all the forces we have. First and foremost, we have some sort of applied force going in the north direction. And I'm going to put this as FA. And I'm just going to say it's equal to 15 newtons. Now, we don't have to include the magnitude here. We could just say it's an FA, but including the magnitude is because we have so many other forces going on here that are all FAs. Now, proportionally, there was a force that was going 25 newtons in the east direction. So I'm going to say this is our FA is equal to 25 newtons in the east direction. And I should make sure I have my vector symbols on here because we need to know that these things are directional. And then lastly, in blue, I'm going to show that angular newtons or the angular force, and I'm going to do it in the following way. They said that it was east of south, so I know it's going to be in the fourth quadrant. And I would have phrased it exactly like that in class. I would have been like, you got to draw this in the fourth quadrant because east and south are sandwiching the fourth quadrant. Now, in class, what I asked you is I said, where does the degree belong? If this is east of south, is it here or is it here? And you should correctly say that the angle belongs below the blue line, and here's how we would construct it. I'm going to go south by some amount. I'm going to go east by some amount. And that's going to give me the overall resultant, or that 20 newtons I was looking for. So I'm going to fill this in as 20 newtons. We know that there is an angle on the interior here. And then the two components of this are going to be the following. We have an FAY and we have an FAX. So very, very critical we put those two things together here. Now, here's where we have to start with this problem here. Besides, and this is one thing I'm going to add before we actually continue here, is we have positive, we have negative. When we look at the up and down motion, we have positive in the up direction, negative in the down. So this is just basically indicating what's happening on the Cartesian plane. Now, our first step is to break apart the triangle in terms of its x component and its y component, or else we can't add up the vector sums here. Now, I'm going to write FAX using the vector symbol is equal to, well, from our triangle, you see that FAX is in the sine position because it's opposite over hypotenuse. So I'm going to write this as 20 newtons multiplied by sine 30. And this is going to give us some sort of value. That value of FAX is equal to, I believe, positive 10 newtons. Let me just confirm that. Yes, positive 10 newtons. Now, for the second piece, I'm going to do FAY because we want the y component of this one. It's going to be equal to 20 newtons. And as soon as you use sine, you know it's cos because, well, not only is it in the adjacent over the hypotenuse position, but it's also the fact that we've already used sine and it can't be sine and sine. So this is going to be cos of 30. And when we write out the magnitude, you're going to get FAY, which is equal to, and then when we put this in our calculator, I believe we get negative 17.32. Now, you're probably not going to get the negative, but the negative comes from the idea that we have to have directional magnitudes here. So this is going down. Meanwhile, that means it's south. If this is going east, that means it is positive. So we see a positive for the x, a negative for the y component. Now, once we have our components, just like we did in kinematics, our step number 2 is going to be actually summing up all the x values, summing up all the y values. So I'm going to take the net of the horizontal, which means I'm going to take the sigma, or the sum of x. This is going to be equal to positive 10 newtons, which was our x component, or FAX. I'm going to add that to the positive 25 that already existed there, and this is going to give me a sigma x, or the sum of the x values, equal to positive 35 newtons. Okay, now I'm going to take the sum of y's, or the sigma of y. when I take the sigma of y, it's equal to the FAY in the downwards direction was 17.32 newtons. The vertical component above was 15 newtons, but it was positive because it was heading in the north direction, and therefore the sigma, or the sum of the y values, is equal to negative 2.32 newtons. Now, here's where things get really important for us. We want to highlight or star these values, and the reason is because they tell us a lot about where this triangle goes or where the values go next. So based on the amount of room we have here, what I might do is just actually open up another page here just so that we can put it all together on that next page. So I'm going to insert a blank page here, and here's what we're going to do. We have positive 35 newtons in the east direction. So I'm going to draw a vector arrow in the following way. Then I'm going to draw my south vector, which was a lot smaller. So this one was negative 2.32, and this was newtons. This one was positive 35 because it was in the east direction, or the horizontal direction. And therefore, we can actually put together our F net, or our net force arrow, which would look like the following. And so I'm going to put this as F net with the vector symbol on it. And I'm going to put our angle here. Now, here's two things we need to figure out. What is the net force based on this triangle, or what is that red F net? The other thing we need to figure out is the angle. To figure out the angle, I'm going to go theta is equal to tan inverse of the opposite, in this case, which is 2.32, divided by the 35 newtons, which is in the adjacent position. Now, as an angle, this is going to give us the following, 3.79 degrees. Now, I know that this problem has two significant digits. Don't worry. We're just going to hold on to this extra decimal place, and then in the end, we can always round this. To get the F net, what we're going to have to do is use Pythagorean theorem. Now, Pythag says that the F net, or the hypotenuse, is equal to the square root of the two other sides squared. And so I'm going to write this as positive 35 newtons squared, plus we have 2.32 newtons squared, and this is going to give us a resulting net force, which is equal to, and for this one, I just want to make sure I get my decimal right, it's 35.08 newtons. Perfect. Now, this is not the full solution. Us solving for the F net and the degree, that doesn't summarize the problem. The problem actually asks for, what is the acceleration? And so what we're going to do is we're going to look at this and say, okay, therefore, here's my overall F net, or here is my F net statement. F net is equal to the mass times acceleration. Now, we want the acceleration, so we don't care to have the mass on the right-hand side. We're going to divide it away, and it's going to give us the following statement. We have acceleration is equal to the F net, or the net force, divided by the mass. Now, substituting values in, we get acceleration is equal to the net force, which was 35.08 newtons. In the bracket, though, because this is a directional net force, it's not just in some sort of simplistic vertical or horizontal direction. We said it was 3.79 degrees. And in class, this is what I would have asked you. If I look at the construction of this triangle the way it is, what quadrant would this be in? Well, if this is the origin, that would mean that the cross-sectional Cartesian plane would look like this. You're in quadrant 4. And so what we're going to do is we're going to go down here and say, if I look at this, the red theta is south of the east line. Or to get to the net force, it's south of the east line. And so we're going to say 3.79 degrees south of east. There we go. Excellent. This is all divided by the mass of this problem. And let me just clean that up a little bit because I made a bit of a mistake. The mass that we're going to divide this by is 5 kilograms. There we go. And therefore, the acceleration we're looking for is the following. 35.08 divided by 5, it's going to give you something like 7.016 meters per second. Instead of doing that, because we want two significant digits, it's going to be 7.0 meters per second squared. And then in the brackets here, what we're going to do is 3.8 degrees, because we only want two significant digits south of east. Now, again, you could answer this using the complement method, but just based on the triangle construction, I'm going to leave it as this. And again, we need two significant digits, so that's why we get this. And what I would do is we took newtons and divided them by kilograms, and apparently that gives us acceleration, or meters per second squared. Try that out on your own. Look back and be like, if I look at newtons and the units of newtons, and I divide it by a kilogram, will I simplify to meters per second squared? And hopefully you should. We actually derived that in class. All right, now we're going to go back to our third example here. Our third example is the following. We have some sort of eastward force that is applied for 2 seconds to a 50 kilogram object starting from rest on a level surface. If there's a frictional force of 50 newtons, what is the resulting displacement of the object? Now, with this type of problem, the immediate thing we should be thinking about is we're now introducing dynamics with a crossover of kinematics. And from now on, like when we go in unit B, C, and D, and we finish out the physics 20 year, you're going to be thinking that now there's this direct correlation or direct crossover between the material we learned in the first unit and the second unit, which is all forces. So here's what we're going to do. I'm going to label the variables. They tell us that we have an eastward applied force. So right above this force here, I'm going to say that this is the FA, or 130 newtons is the FA. It's applied for 2 seconds, meaning this is our change in time. The 50 kilograms is our mass, and then they give us one of these rules or one of the implied values from earlier in kinematics, and we said if an object starts from rest, it means its initial velocity is equal to 0 meters per second. So that might be an important thing to include here. Now, it's on a level surface with a frictional force, or an FF, equal to the 50 newtons. What is the resulting displacement of the object? So this would be D is equal to question mark. Okay. Now, what we need to be thinking about is, first of all, free body diagram. So I'm going to draw in a free body diagram where we draw out a level surface. Here's the level surface. I'm going to draw some sort of object on that level surface, looking like this. And now we need to fill in all of the vectors according to this diagram. So we have some sort of eastward or east vector that represents the applied force. I'm just going to make sure that arrow looks a little better. There we go. So this is our FA. We then look on the reverse side, and the reverse side says that we have some sort of frictional force, which is a lot smaller, or a fraction of it, and we're going to say that this is our FF. And then the two other forces that you may easily forget are the following. We have some sort of FG, because this is being pulled down to the Earth's surface, and we have some sort of Fn, or normal force, which is the force that responds to the surface contact. Okay, and again, Fn and Fg, these things are balanced because otherwise, if the Fn was greater than Fg, this object would be flying away into the sky, and if Fg was greater than Fn, it would be crashing through this horizontal surface. So we don't want to propose either one of those. Now, what I'm going to do is I'm going to put in the indicator of which direction is positive and negative, and we're just going to follow the regular Cartesian method of positive is in the right x-axis, negative is in the left x-axis. Now, to solve this, what we want to do is we could do the following. We could either solve for the net force right away and then plug it in, or we could combine all the steps together to get our acceleration off the bat. And that's maybe what we'll do here. So we created our free body diagram. What I next want to do is say F net, or the net force, is equal to the FA, or the applied force, plus the force of friction. Now, we know that when we add these forces together, it's going to give us the net force. We don't need to include Fn and Fg because they're balanced and they would cancel out. They're equal and opposite forces. Now, I'm going to expand the definition of Fnet and say mass times acceleration is equal to the Fa plus the force of friction. We're going to divide away the mass to both sides, and this is going to give me acceleration is equal to Fa plus the Ff, all divided by the mass of the object. And now we can just plug in numbers to get our acceleration. Acceleration is equal to, in the FA, it was positive 130 newtons because it was in the east direction, plus the frictional force. We just want to make sure we get this right here. If I look at my frictional force, it was negative 50. And so I'm going to go negative 50 newtons here, divided by the mass of the object, which was 50 kilograms. Now, if you add your forces together and you get the net force, this is actually equal to positive 80. And positive 80 divided by 50, this gives us an acceleration equal to positive 1.6 meters per second squared. Now, why is it positive? Because if we look back to our FNet diagram, or our free body diagram, you clearly see that the FA is greater in magnitude than the FF, and thus the acceleration is going to be in the direction of the FA. Now, the one step we're going to need to do with this, and maybe I'll do it on the same page because we actually have enough room down here on the left here, is I can take this acceleration and now pass it forward, or pass the torch of this over to the kinematic side. We've done the dynamic situation we needed to. We've got our acceleration. Now we're done with dynamics. Let's pass that information forward to kinematics and the study of motion. So for our final step, we're going to say, based on the criteria of this, I could write out VI, VF, acceleration, change in time, and change in the displacement. Now I'm going to say equals, 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 and then making sure I have my vector symbols, all my velocities. Well, VI was 0 because this object starts from rest. VF, they didn't really mention, so I'm just going to kind of ignore that for now. Acceleration was positive 1.6, and that was the acceleration we just found from our overall net force. The change in time, or the time spent in this travel, is 2 seconds. What is the displacement? Well, what we can do is, just like we did in kinematics, we look at this and we say, uh, which equation that is, which equation matches up this description here. And the equation that matches up this description where VF doesn't matter is the following. Displacement is equal to initial velocity times time plus 1/2 AT squared. There we go. Now, from here, right away, we can wipe out the VIT because we know that VI is 0 and anything times 0 is just going to cancel. And this is going to leave us with displacement is equal to 1/2 times the acceleration, which was positive 1.6 meters per second squared, multiplied by the time squared, which was 2.0 seconds squared. And if you do the math in your calculator, therefore the overall displacement is equal to, and remember, we got 2 significant digits throughout this problem, it's going to be positive 3.2 meters, or the other way we can say this is 3.2 meters. Based on the way we wrote out this and based on the context of the problem, 3.2 meters east. Both of these values would be completely acceptable, and either one could appear in a multiple choice, so you got to be worried with that or just be a little careful with that, but other than that, we're good. Now, this is a very common thing. When we look at this problem, it's very common to be solving for the acceleration first because the acceleration is the connection between the net force and the kinematics that we may be studying. So don't be surprised if your step number 1 is always solving for this acceleration and then being like, hey, take that acceleration and pass it forward. This is no surprise to me, and it shouldn't be any surprise to you moving forward. All right, now our very last problem is number 4 here. So we look at number 4, and number 4 is a problem that deals again with kinematics and says, if I give you some information revolving around the study of motion or kinematics, and I give you a little bit of information that wants us to study the forces or the dynamics at play, how can we put these things together to help us figure out an answer? Now, right away, we're just going to label a couple variables. They say that this car comes to a stop from a speed of 25 meters per second in a certain change of time, that being 6.5. What is the braking force required? So right away, I'm going to label this as my mass. Comes to a stop. Well, this is one of our key assumptions that says that the VF is actually equal to 0 meters per second. We're given a VI, which is equal to this 25 meters per second, and then we're given some sort of change in time. What is the braking force? Well, let's actually explain what braking force is, because I think it's really important that we really establish what it means to be braking force, because it's not just simply force of friction. Let's draw out our free body diagram. Here it is, and I'm going to draw some sort of car that's over top of this. So just a basic box, couple wheels there. There we go. Now, they don't give us any information about the forces, but what they do tell us is the following. If this object is coming to a stop, we have some sort of engine force, which is this FA. The FA is causing the general motion forward. If it's coming to a stop, it means the force of friction must be greater than the force applied by the engine, or else this thing would just continuously go in the forward direction or stay at a uniform speed or be at rest. If these things were balanced, that is, that would be first law. But in the case of this being a Newton's second law problem where the forces are unbalanced, forces that are unbalanced, we need to take a closer look at this. Before we do that, I just want to make sure I label in 2 more forces here because they're also important for the problem. FG and FN. Because again, this is a car that's on the horizontal. We're not in the Jetsons. It's not flying off in the sky. We're not talking about an airplane that has no sort of overall FN or contact force. So we got to label those in there. If you don't label those in there, you're missing a key critical detail. The other thing I want you to write in here is the following, that this is going to be positive and this is going to be negative, or the other side going left, the opposing direction is negative. Okay, here's what we're going to look at this, and I want you to take a closer look at what it means to be a braking force. Suppose that I highlighted this, FA, and the component of FF that would represent the length of FA. If I highlight those 2 yellow pieces, you're clearly like, okay, well, there's at least the same magnitude of FA in the FF on both directions. So we see in the left and right direction, there's at least that same amount of force or the same amount of newtons. Where the braking force comes in is the following, and I'm going to highlight it in blue. This little section, the extra piece, the extra amount of newtons that are in that left direction, these determine the braking force and thus are actually the net force. And so it's really important. I'm going to even circle this here, right here. This component here, this is equal to our net force, F net. And in class, I even called this the FB, which is the braking force. And so when we go up and say the braking force, what we're really asking for is the net force. And I'm going to just draw that out in black to match the rest that is up here. So this is the F net. Perfect. So the extra little piece that is that force of friction is actually the difference that makes up this net force, or is considered to be the braking force and the reason this thing is unbalanced. Otherwise, if the blue part didn't exist, or that little extra bit of force of friction, the object wouldn't be braking, it would just be moving at a constant velocity, or it would be completely stopped. And so this extra little bit causes it to slow down. Now, that was a little bit much because I probably went into detail on that a couple times more than you needed, but it's really, really important to emphasize that braking force is not just simply all of the FF. It's that extra little net force that goes into this. Now, what we're going to need to do is solve for our acceleration right away, because the information that we have indicates that we have a lot of information from the kinematics piece and not a lot about the forces. And so in order to calculate what the braking force is, we're going to have to use some kinematics first. So I'm going to say for step number one, or part number one here, I'm going to solve for the acceleration using the basic acceleration equation from kinematics. Vf minus Vi divided by the change in time equals acceleration. Acceleration is thus 0 meters per second, which is the final velocity, minus the positive velocity, which was 25 meters per second in the forward direction, divided by our time, which was 6.5 seconds. Now, those of you astute students should notice the first thing right away is that the acceleration should be negative because it's going in the direction of the net force. What is the direction of the net force? It's in the negative direction, or in the left direction. So I'm going to write this as negative 3 point, and then my numbers that I'm getting for this are 846 meters per second squared. There we go. Okay, and then, or what we could write here is using directional method, 3.846 meters per second squared in the west direction. Both of those would be okay. Now, again, these aren't final solutions, so I'm not going to be super particular about if you use negative or west, but just for your own sake. Now, to finish out this problem, we have to take this acceleration and pass it forward and say, okay, now we're going to go from kinematics to dynamics and say that our overall net force, or F net, is equal to the sum of these forces. We have FA, which is in the forward positive direction, plus FF, which is in the opposite direction. And now I'm going to expand out the definition of this. Well, actually, I don't want to expand out the definition of this. Rather than writing the combination of these forces, because I have the acceleration, I can actually just write this as F net is equal to mass times acceleration. And because I know the mass and the acceleration, let's just plug those in. The mass is equal to 1,200 kilograms. Pretty typical car weight. Multiplied by the acceleration, which is negative 3.846 meters per second squared. Close the bracket. Therefore, the net force, or the force that's causing this to break, is equal to, and I'm even going to put that in there, FB, the braking force, is equal to, if I actually expanded this out and multiplied it, I would get negative 4,600 in terms of newtons. But I actually want this to 2 decimal places here, and there actually might even be different numbers here in terms of the 100. Like 4,600 is a pretty general marker. So instead of writing 4,600, I'm just going to use the 2 significant digits and make this negative 4.6 times 10 to the 3 newtons, which would mean that this is ultimately 4,600 newtons, but the number is probably just a little bit more complex than that. So I don't want to just say 4,600. There's probably a couple digits in there that I haven't calculated recently. So I'm just going to write this as 4.6 in the negative direction. And therefore, this is our net force, or the braking force. All right, now this is where you go on to the practice problems. Very, very critical that you try these out on your own and that you're actually working with these free body diagrams and this new idea where we have Newton's second law that says an unbalanced force causes some sort of acceleration in the direction of that unbalanced force. And now we have this ability to go backwards and forwards between dynamics and kinematics, and they handhold each other using that acceleration.